Okay, is everything working well?
Yes.
Excellent. All right, so good morning and good afternoon, everyone. And I'm sorry I cannot be there in person on either side of the Atlantic today. So I would like to thank the organizers to make sure that this conference keeps happening. We had the first series of debates 2 years ago. That was super interesting. I had the pleasure to give the closing remarks of that conference. And today it's really a pleasure to open this second iteration of debating the potential of machine learning in astronomy. So what I'm going to do during this talk is to give a quick overview of some of the things that have happened in the field in the past 2 years. And I'm mainly going to raise some questions, which I hope will influence the way some of you might present your talks, do future research, and some of the questions that are going to be raised during the debates. All right, so here is an overview of the literature over the past 23 years. What I'm showing here is the number of referred papers in astronomy only as a function of time. And so this is telling us a couple of interesting things. First, if we think of machine learning as a field, we see that today it is of comparable size as the field of exoplanets. If we think of machine learning as a technique, as a data analysis technique, today it is as widespread as Bayesian statistics, okay, which have basically percolated throughout astrophysics. The difference is that the machine learning phenomenon in astronomy, as you can see in this figure and as you well know, is very new. Everything happened over the past several years. There's another difference I'd like to mention here, is that in contrast to exoplanets, where we astronomers are really driving the field and are the only players in the arena, when it comes to machine learning, we are tiny players in a huge arena. And often we are actually just trying to catch up with what's going on out there. Many of the techniques we use are designed by computer scientists or people in industry. And that's another major difference with what we are doing, for example, in the context of exoplanets. I will come back to this during the talk. Right. So why are we so excited with machine learning? And so my view of this is that this allows us to deal with complexity. Here are different objects we encounter in astronomy, 1D objects, 2D objects, or fields in general. And they are ordered along this apparent complexity axis. If most of your work is on the left side of this axis, typically you can do most of what you need to do using Gaussian statistics. However, as we move towards the right, and if we increase the level of complexity, what happens is that very quickly we find the limits of the statistical language we use using classical statistics. And a different mathematical language, a different way to interact with data is needed. And that's really what neural networks allow us to do. So why do they work? So here I think two key points. I'm getting some echo here. The architecture of neural network enables to basically have two things. One is geometric stability, and I think that's really what is key here. That's the ability to have robust estimators that are robust to small perturbations of the input data. And the second one is to have the ability to include symmetries. Data can exist over different domains. Here we have, for example, the grid, the most common in astronomy when you use pixel data. But as you can see here, we have other examples, for example, graph and manifolds. Each of these domains comes with a possible symmetry or symmetries that are listed here. And for each of them, we basically have corresponding neural network architectures that enable us to perform calculations with geometric stability and the corresponding symmetry. This is why there is a zoo of architectures out there. I've listed some of them, convolutional neural networks, for example, or graph neural network here. And so this is what's going on. As time goes on, this list keeps increasing. And as astronomers, it's always quite challenging to keep up with all of them. So we can deal with complexity in different ways. For some of us in astronomy, complexity is in the signal. For example, if we are trying to characterize the morphology of a galaxy, the spectroscopic signature of many absorption lines or a time series, complexity can be in the signal. But for others in astronomy, complexity is in the noise or the instrumental response. This is often the case, for example, with exoplanet detection. The image I'm showing here is an example of high contrast imaging. Here, the exoplanet is going to be just a couple of pixels in the image. And so with such a limited number of pixels, clearly we cannot have any complexity. However, what you can see is the rest of the image shows the tail of the PSF due to the really bright star that is next to the planet. And the challenge here is to be able to detect these couple of pixels associated to the planet in this sea of complex fluctuations that are due to the star, as well as effects of the atmosphere and the instrumental response of the telescope. For space-based astronomy, we have also seen examples of intra-pixel variations that are actually quite hard to describe with classical techniques, but here again, machine learning can help and model this complex behavior. There are other aspects of complexity that are more conceptual. Sometimes we have to deal with non-Gaussian likelihoods, for example. We are going to see during this conference more use cases of graph or tree manipulation. I'm going to comment also on long-range high-dimensional correlations, which are emerging in astronomy. We sometimes have to deal with complex high-dimensional latent spaces. I will talk about this as well. And finally, we can use machine learning to analyze the literature as a whole. The good news is that for all these challenges, we now have new tools available. I'm going to go through this list. This is not an exhaustive list, but what I've noticed by comparing the talks given this week compared to the talks given 2 years ago, those are some of the key techniques that have been emerging in recent times. So let's go through this list. For example, simulation-based inference. This is also called likelihood-free estimation. It's now widely adopted, and we are going to have many talks this week showing how this technique can be used to basically go from the simulation of a complex field to the estimation of its parameters. So basically, this is saying that the problem of statistical estimation for a phenomenon we can simulate is more or less solved, sorry. This was not the case if we go back in time, but we are approaching now a situation for which this is no longer the bottleneck of any analysis. But so far, this has mostly been used on simulated data. One still needs another step in order to go to actual astronomical data. And I'm going to take this opportunity to mention one example of this kind of simulation-based inference in the context of weak lensing. So what I'm showing at the top is a mass map, a kappa map, simulated. And the typical exercise here is to estimate some cosmological parameters from observations of such a map. Classically, it used to be done mainly through a power spectrum analysis. Several years ago, some people showed that by using a CNN to perform this mapping, one can have a much better statistical power. So that was interesting. That made a splash. This was a Nature paper. But later on, some of us showed that the same type of result can be obtained without a neural network. And this is an example using the scattering transform, which is a fully deterministic estimator. And some of us showed that it is possible to reach roughly the same performance. In the context of the scattering transform, one can only manipulate 40 parameters, as opposed to the 1 million parameters that need to be trained with a CNN. And I think, almost everyone will agree that if we have to choose between these two estimators, it seems much more favorable to use a fully deterministic estimator, which manipulates much fewer parameters than having to train a neural network and use a black box we cannot fully control. Interestingly, this was not the end of the story. When it comes to estimation, recently, BYD and Urs Seljak showed us that we can actually reach an even higher level of performance, this time using multi-scale flows rather than CNNs. And I would like to just comment on one point here, is that we have to be careful. Scientific machine learning is different from the type of problems that are used in industry. And using out-of-the-box architectures is often not the optimal solution for us. So I just wanted to comment on this. There was going to be a talk later this week talking about this multi-scale flow approach. But we should keep in mind that, even though we can do better with out-of-the-box architectures, this doesn't mean that we are reaching the best possible performance. And so we have to go back to the basics and really think deeply about the architectures we use to make sure that we can actually get the best out of the data we have. I'm going to continue and talk about graph neural networks. We are seeing more and more applications of those in astronomy, and I'm citing two examples here: density field estimation and cosmological parameter inference. This is based on characterizing the distribution of halos using a graph as an estimator of the density field. We are going to hear a talk about this in a day or two. There have been interesting applications of graph neural networks in the context of galaxy merger trees. This is quite nice because historically, merger trees have not been studied so much, considering applications that link both simulations and data. And so the ability to manipulate these merger trees with neural networks allows us now to basically assign a merger history to a galaxy just based on observational data. I think there is an interesting avenue here that is definitely worth pursuing. If we continue, we've seen now the emergence of transformers in astronomy, mostly for time series. There would be many papers and many people to cite here. I'm just going to mention that there are interesting applications in stellar time series analysis, as well as in exoplanet detection. Moving on, we are hearing more and more about foundation models. So what are foundation models? They are models trained on broad data at scale. And they are adaptable to a wide range of downstream tasks, which means that they are not designed for one specific task, but they are basically the starting point for many possible tasks that can be built on. Many of these models, they are the GPTs, the BERT, the DALI, etc. What is interesting is that this trend is now coming to astronomy and is being applied directly to astronomical data. So what do I mean by this? So to illustrate this, I'm going to take this example. This is a very nice result using contrastive learning, and that's a few years old. The idea is to basically create a manifold that would represent the data distribution. In this case, we are talking about images of SDSS galaxies. And what is quite nice with this approach is that with a very simple formalism, one can automatically embed all the data on this manifold, which is not necessarily low dimensional. I'm just showing here a two-dimensional projection of it. But what is interesting is that this is quite rich and is a very interesting starting point for the global data analysis of the data. These types of approaches are extremely flexible, and it's now possible to combine data from imaging, data from spectroscopy, data at different wavelengths, combine them all together to create one common feature space, one manifold that is then the starting point for data analysis. And here we are seeing a very interesting phenomenon because we are basically skipping the process of source catalog creation. One can go directly from the raw data, pixel data, to this embedding without having to, at any point, manipulate a full source list. And so what we are seeing here is that we have a new entry point for data analysis in astronomy, and the new generations are going to enter the field by being exposed and by manipulating a type of objects that we previously did not encounter at all. It was basically our job to take these catalogs of sources and, using some statistical analysis, create these manifolds, but now this can be done automatically in a very simple manner. If I take SDSS as an example, the mapping from the pixels to parameters was done thanks to the hard work of Robert Lupton, who wrote the photo pipeline, which for each source extracted a list of parameters. Only Robert Lupton knows exactly what's happening in this photo pipeline. And the list of parameters is usually sufficient for sources that are not very well resolved. But as we consider more and more complex objects and more resolved galaxies, for example, this list becomes only a partial view of the data. The advantage here is that we have a much more complete view of the data, and that the generation process of this manifold is described in a very simple manner and accessible to everyone. So I think there is an interesting transition here. We might perhaps abandon these source catalogs in the future and work directly with these embeddings. Large language models, I have to talk about them since we are now in a post-ChatGPT world. There are interesting attempts in astronomy. There is the University collaboration that has used a pre-trained language model and fine-tuned it to the astronomy literature. What can we do with this? You can do what all of you try to do with ChatGPT, for example. The idea, you can start with a prompt and ask the system to either answer your question or continue writing. So this is an example where someone starts to write the beginning of an abstract with the beginning of an idea, and the language model continues and proposes the rest of the abstract for this analysis, which is actually quite interesting and quite plausible. So this is a new tool, and I think it is quite exciting because for the first time, we have the ability to interact with the literature as a whole. What you are seeing here is a map of all the papers that have been posted to arXiv over the past 20 years. Every dot in this image is a paper. Your papers are going to be there. The number of papers is quite sizable. It's of order 10 to the 4. And nobody, of course, has the chance to scan all of these papers. And so now what is interesting is that these language models fine-tuned to astronomy have read all these papers and can meaningfully, for example, propose hypotheses of ideas that could be interesting to explore. So I don't know how interesting this is going to be, but I think there is a very nice potential, and I hope we are going to discuss this more later during the week, during some of the debates. What can language models do for astronomy? It's a real question, and I look forward to seeing what people have to say about this. So the great news is that we have all these new tools in the field, but now I would like to step back and take a moment to reflect on this. The perception of machine learning in astronomy is quite bimodal. So what's happening? Some people are not so enthusiastic, and that's actually why we're here, not to talk about the potential of ML, but to debate the potential of ML in astronomy. So on one hand, we have these new tools, and we've been writing lots of papers, but there is a very legitimate question. Has there been any major discovery? Of course, there are many ML-enhanced results in the field. We've seen many, we will continue to see some. The question is, has there been any ML-enabled discovery? Has there been any impacts? Have we come up with a new physical understanding of the universe so far? Before this conference, during the past couple of weeks, I've asked many of you to answer this question. And overall, the typical answer is not really. I think we all agree that in astronomy, we have not yet had our protein folding moment. Okay, that was a very clear moment in biochemistry for which one result was truly ML enabled, but we are not there in astronomy. Interestingly, we now have at hand tools that we were dreaming of 10 years ago, 20 years ago, to explore our data sets. But with all these powerful tools, we have not found any new type of objects. We have not really found any new physical trends with a significant impact in the field. And some of the techniques, for example, saliency maps, have only rediscovered what we already knew. So there is a question here. What is happening? What is the reason why no major discovery has been made so far? Is it that classical statistics are good enough in astronomy to go a long way? Perhaps the nature of the objects that we study is such that this is the case. Or perhaps is there a mismatch between machine learning techniques and astronomical data? So what do I mean here by this is that perhaps astronomical data is not complex enough. If we compare it to data we found in other fields, for example, remote sensing or just natural images, we in astronomy tend to be at the bottom of this complexity axis. And perhaps as a result, we are not fully benefiting from the power of these machine learning techniques. Or is it the case that if we take simulation-based inference, for example, the technique is so powerful and so sensitive that when it comes to being applied to data, it is extremely challenging and too sensitive to data drifts? Or finally, this is the view of many people in the room actually, we are still in a phase in which we are building tools. And perhaps it will simply take a little longer before significant discoveries will take place. I would like to briefly advertise Euclid, which basically was designed originally at the IAP by Yannick Mellier. Euclid is producing beautiful data. Euclid was designed without any machine learning in mind. Now the key question, and I hope we are going to discuss that this week, is that what is ML going to do for Euclid? Are we going to see ML-enabled results with Euclid, or will it remain in this classical regime that we've seen so far? All right, my time is almost up, so I will conclude with some final thoughts. First, I would like to say that I think this is a very exciting time. Okay, it's been very exciting for me, at least. We have new ways of thinking, new ways to deal with complexity. We were dreaming of these tools years ago. We now have them. We can interact with simulations, with data, with graphs, with time series, with the literature in new ways. We are seeing many ML-enhanced results. This is exciting, but so far, we have not yet seen an actual strong impact on our physical understanding of the universe. What's going to happen with machine learning is still unclear. And that's why we are here to debate the potential of machine learning in astronomy. And that's why it's taking even a second iteration to reach some interesting conclusions to these questions. And so with this, I would like to open the conference, and I look forward to all the scientific talks as well as the debates we are going to have this week. Thank you.
Thank you very much, Brice.